Have you ever stopped to think about what's actually going on inside the device you're watching this on right now? I mean, it's not magic, right? It's this secret world, a hidden journey with its own language and its own rules, all happening faster than you can blink. Well, today, we're going to decode that secret. We're going to follow the life of a single electron as it finds its way through a circuit. So here's our game plan. First, we're going to learn the basic language, the symbols of the circuit. Then we'll meet the electron and figure out how we measure its flow. After that, we'll get into the rules of the road that tell it where to go, check out the different paths it can take, and finally, see how it all comes together to deliver power and, make things work.
All right, let's just dive right in. If you want to understand any story, you've got to know the alphabet first. And in electronics, that alphabet is made up of symbols, and each one represents a key character in our little drama. Let's kick things off with a switch. Think of it like a gatekeeper. When that switch is closed, the bridge is down, and our electrons have a clear path to run along. But when it's open, the bridge is up, and everything grinds to a halt. It's a simple idea, but it's absolutely fundamental. Next up, one of the most important destinations for our electron, the lamp. Its whole job is to take the electrical energy that the electrons are carrying and just transform it. The current makes a tiny wire, the filament, get super hot until it glows, turning all that invisible energy into light and heat that we can actually see and feel. And now, meet the resistor. This component is basically a roadblock. It's like a deliberate traffic jam or a really narrow street in our circuit. Its entire job is to slow down the flow of electrons. And that makes it an incredibly important tool for controlling exactly how much electricity goes where. Okay, so we've met some of the main characters. Now let's meet our hero, the electron. Or to be more accurate, trillions and trillions of them. This part is all about understanding their movement, this massive river of electricity. So it all starts with something called electric charge. This is the basic property that lets electrons move around and carry energy in the first place. And we measure this charge in a unit called coulombs. So, just how much is 1 coulomb? Well, it's about 6¼ quintillion electrons. That's a 6 followed by 18 zeros. The scale here is just mind-boggling. We're not talking about one electron doing its thing. We're talking about a massive, coordinated army of them. So if the charge is the water in our river, then the current is how fast that river is flowing. We measure it in amperes, or amps for short. And 1 amp is just that giant army of electrons, 1 coulomb's worth, flying past a single point in the wire every single second. And believe it or not, we can calculate this flow very precisely. The formula is actually pretty simple. Charge equals current multiplied by time. So if you look at this example, if we've got a current of 1.5 amps flowing for a full minute, a quick bit of math tells us that 90 coulombs of charge have gone by. Okay, so we know our electrons are flowing, but what's making them move in the first place? And what's trying to slow them down? Well, every journey has rules, and in a circuit, it all comes down to 2 key forces: the push that gets things going and the squeeze that holds them back. Let's break down these 2 forces. On one side, you have voltage. This is the push. It's basically a measure of how much energy each little electron is given to make its trip. On the other side, you have resistance. That's the squeeze. It's the opposition to that flow, and we measure it in ohms. So voltage wants to push, and resistance wants to, well, resist. Now, the relationship between this push, the squeeze, and the flow that results from it is described by probably the single most important rule in all of electronics: Ohm's law. The official definition is right there, but what it really boils down to is this: if you push harder with more voltage, you're going to get more flow. Simple as that. And here is that beautiful law in action. The formula is voltage equals current times resistance. So if we know we have a 2 amp current flowing through a resistor with 40 ohms of resistance, we can figure out that it must take an 80-volt push to make that happen. It's really elegant. All right, our electrons know the rules of the road. Now they have to actually navigate the layout of the circuit. And there are really 2 main kinds of road systems they're going to find, one with just a single lane and another that has a bunch of forks in the road. So in a series circuit, there's only one path, kind of like a 1-lane road. That means the current is exactly the same everywhere, but the voltage, that push, gets shared among all the components along the way. But in a parallel circuit, the road splits. The current actually divides up. But, and this is the key part, the voltage is the same across each of those separate paths. And this slide shows you the wild difference between these 2 layouts. Just look at the real data.
If you put two 10-ohm resistors in series, the total resistance just adds up. You get 20 ohms. Makes sense. But, and get this, if you put those same two resistors in parallel, the total resistance plummets to just 5 ohms. By adding another path, you've actually made it 4 times easier for the current to get through. So what's the whole point of sending these electrons on this crazy journey anyway? Well, the ultimate goal is to deliver energy to do some kind of work, right? Whether that's lighting up a room or running a supercomputer. And the rate at which we deliver that energy is called power. Electrical power is just the measure of how much energy is being transferred every single second. See, it's not just about having the energy, it's about how quickly you can use it. We measure this in watts, and that's why a 100-watt bulb is brighter than a 60-watt bulb. It's converting more energy into light every second. And you guessed it, there's another simple formula for this. Power equals current times voltage. So if your lamp is pulling 2 amps from a 230-volt wall socket, it's using 460 watts of power. That means 460 joules of energy are being zapped from the outlet to your lamp every single second. Okay, remember Ohm's law, our golden rule? It said that resistance is supposed to be constant. And for a simple component like a fixed resistor, it is. We call that an ohmic conductor. But a lot of components, like that filament bulb we talked about, actually break the rule. As the voltage across the bulb goes up, its resistance doesn't stay the same. It actually increases. So why on earth does that happen? Well, as the current flows through that tiny filament, it gets insanely hot. That heat makes the atoms inside the wire, the ions, start vibrating like crazy. For an electron trying to squeeze through, it's like running down a hallway where the walls are shaking uncontrollably. You're going to bump into them way more often, which makes it harder to get through. And the result? Resistance goes up. So from a simple switch to this complex dance between voltage and current, this whole secret journey is happening billions, trillions of times every single second, right inside the screen in front of you. It's the hidden language that runs our entire world, which really only leaves one question. Now that we understand the rules, what are we going to build with it next?